Welcome to this short explainer video about orbital energy. What we're going to do is go through some equations which look at the expression of energy of a satellite as it orbits about a fixed radius. In doing so, we're going to be taking some of our concepts from mechanics, some of our circular motion, and then combining it with our IB fields topic. So there's really a lot going on in this. Make sure you have a pen and paper and be ready to take some notes. First things first, we want to remember a little bit about our circular motion topic. So we'll remember that when our satellite is in orbit around, say, the Earth, it could be about a moon, it could be about Jupiter, we're going to assume that we're in a circular orbit. Okay, and the question we always ask ourselves when we're doing circular orbit is, what provides the centripetal force? Well, in this case, it's gravity. And we're going to use this fact to derive some energy equations for this situation. So you can see here that our good old equation from the circular motion topic was that the centripetal force, mv squared over r, is equal to gmm over r squared. That's our gravitational force. Now, we're going to do something with this equation to think about our kinetic energy. You should be able to see that in the equation you've got there, our kinetic energy is actually almost in our equation. Kinetic energy is a half mv squared. We've got an mv squared and then divided by an r. So I'm just going to do something a bit weird. I'm going to divide both sides of my equation by 2. And the reason for that is I've got my half mv squared on the left-hand side. As long as I divide by 2 on the left-hand side, I've got to divide by 2 on the right-hand side as well. And so therefore I've got mv squared over 2r is equal to gmm over 2r squared. And that's just a little trick that we sometimes use in order to manipulate our equations more. You should be able to see there then, if I cancel a factor of r on the bottom of each of my sides of the equation, I've got that the kinetic energy is equal to mv squared over 2, half mv squared, and that's simply equal to gmm over 2r. Now, we can see there that there's a relationship between my kinetic energy and the radial distance. Specifically, we've got an inverse proportional relationship. That is, if I double r, then the kinetic energy will decrease by a factor of 2. So if we're wanting to calculate kinetic energy, there's 2 ways we could do it. We could use mv and square and then divide by 2, or we could take gmm over 2r. And we're actually going to use that second expression in the rest of the derivation. We remember here that the total energy is the sum of the gravitational potential and the kinetic energies. So in other words, my total energy is a half mv squared, and I've got to add in my gravitational potential energy. Now remember from previous lessons, our gravitational potential energy is the product of the potential and the mass, and that comes out as minus gmm over r. You should be able to see here that there's a similarity between our expressions for kinetic and gravitational potential energy, and it is that actually they're both inversely proportional to distance, and they both are directly proportional to the masses involved. And you should be able to see if I substitute my mv squared over 2 with the above expression that I've done in my third line there, and actually I get a very similar expression to my potential energy, the only difference being a factor of 2. So actually I can get a simplified expression for my total energy, which is simply the total energy is minus g times both of our masses divided by 2 times the distance. Now we notice that we've got a minus sign. The total energy therefore is a negative value. And what this means, and it's a very key point, is that the satellite is going to remain within the gravitational field. If we ever find a point where the total energy has a negative value, then what this means is the satellite is in what we call a bound state. Similar to the way that an electron is bound to an atom, as in remains in the electric field of the atom, the satellite is going to remain in the gravitational field of the planet. And we know that via our negative energy. If our total energy is greater than 0, what that means is my kinetic energy outweighs my potential energy, and so therefore I will leave the field. So we're always expecting for an orbiting planet to have a negative energy. Okay, what you're going to do is you're going to take note of these equations, and then you're going to use them in your next exercise, which is all about determining the orbital speed of a satellite in the geostationary position. As ever, I look forward to seeing your work.